Now we're going to take a look at a control volume energy analysis. So this you're very comfortable with. You've done this in thermodynamics over and over again. Hopefully you remember it. So we're going to take a control volume here. I'm going to write the first law. So the first law of thermodynamics, dEdt, change energy for the system. The control volume in this case is Q dot, where Q is defined as positive going in, negative going out, minus work, where work is defined as positive going out, negative going in, plus m dot in times enthalpy, velocity squared over 2, gz in minus m dot out, enthalpy, v squared over 2 plus gz out. Remember that energy is made up of internal energy. This is not velocity in this particular context. There's no way to do this. There just aren't enough letters in the world to handle all the variables when you combine these fields. But internal energy here, kinetic energy and potential energy. But many, many times we're doing this type of analysis, almost every time I've ever seen it, in fact. People are looking at steady state situations. So if you're looking at steady state, that immediately is going to kill this term. There's no time dependence, so that's going to go to 0. And so we're left without that. And also that means, therefore, that m dot in is going to equal m dot out, because if it's steady state, the mass of the system can't be changing either. So in those situations, you end up with the steady state energy equation, which you certainly have seen. Steady state energy equation. So we have 0 on the left because we killed that dEdt term, Q dot minus W dot plus M dot. Now there's only one M dot because it's all, it's both in and out and they're the same. H in minus H out, V squared in over 2, V squared out over 2, and, G times Z in minus Z out. So that's your steady state energy equation. So definitely you want that in your bag of tricks, to use for analysis. We're going to modify this form because a lot of times engineers have used this in the field in a different form. So if it were up to me, this would be the form that everybody would always use. But this field has developed over hundreds of years, and different people have developed different traditions. So we're going to take a little look at some of the other ways people have represented the same equation. So 0 equals Q dot minus W dot plus M dot. We're going to break out the internal energy here. So this little hat, this weird hat, is supposed to indicate internal energy, plus V, P in minus P out. That's your enthalpy terms. Then, of course, you've still got your velocity terms. So there's that, where we've broken out this thing as internal energy. Sorry, internal energy. That's your internal energy. So we're going to rearrange this to put all the inlets on the left-hand side. So we're going to have m dot p over rho, because v is 1 over rho, p over rho, plus v in squared over 2 plus gz all in. And that's equal to m dot, same m dot, but now p over rho plus v squared over 2 plus gz all at the outlet. And then we have minus m dot, where we've broken out the internal energy as a separate term. And I don't really know why they do that. And then, of course, we've still got minus Q dot over M dot and minus W dot over M dot, plus W dot over M dot. Those are your heat transfer and work transfer per unit mass. It's not per unit mass yet. Sorry, we didn't divide by M yet. Now we're going to divide everything by M. Let's see here. Yeah, I did that right. So we're going to divide everything by M dot. So we have just P over rho plus V squared over 2 plus GZ all at the inlet equals P over rho plus V squared over 2 plus GZ all at the outlet. Then minus just U in and minus U out over here. and then minus Q dot. Now it is over M dot because we just divided by M dot, W dot over M dot. So this is a form that's on a per mass basis for this. And basically, civil engineers like to divide this all by G. So we'll follow their lead on this for this part of the class. So we have P over rho G plus V squared over 2G plus Z, all at the inlet, equals P over rho G plus V squared over 2G plus Z, all at the outlet, minus this internal energy change, U in minus U out over G now, very strange term. And then we have the Q terms. But we're not going to call them that anymore. So we would have, minus Q dot over M dot G and plus W dot over M dot G. But that's not the form that they like. So we're going to change it one more time to the final form, which relates everything in terms of what they call head losses. So we're going to call it still, on the left-hand side, P over rho G plus V squared over 2G plus Z at the inlet equals P over rho G plus V squared over 2G plus Z at the outlet. But now we're just going to have three what they call head loss terms: H friction minus H pump plus H turbine. So this is another form of the equation that you see used a lot, I guess, where you have essentially different losses that can be accounted for, account for different factors in the flow. So these all H's are positive. So if you have friction, that's going to cause a loss of energy to the system. If you have a pump, that's actually going to add energy to the system. Pumps add energy. And so that's going to make the outlet, come up higher because you have, this negative sign is going to cause this to have to be larger. And of course, a turbine is going to subtract a lot of energy from the system potentially. That could be the point. So all these three things, that's friction is friction losses, pump energy to flow, and then turbine extraction. So that form of the equation is often used when analyzing those kinds of flows.